Hello, in this video we want to discuss basic results of linear maps. This is a follow-up to what we have learned in linear maps in our previous video. So, stay blessed. Let x and y be two linear spaces over a scalar field k, and let T mapping x to y be a linear map. Then 1. T of 0 is equals to 0. 2. The range of T, R of T, is a linear subspace of y. 3. T is 1 to 1 if and only if T of x is equals to 0, which implies x is equals to 0. And 4. If T is 1 to 1, then T inverse exists under the range of T, and T inverse maps the range of T to x, is also a linear map. These are basic results in linear maps. So let's look at these results. Let's prove them one by one so as to be able to understand more about what we've learned in the linear maps. So start. Now we prove. We start with the first one. Proof. Now let's prove. The first one says T of 0 equals to 0. So you can say since T is linear, T of alpha x is equals to alpha T of x for x in x, for all x in x. Okay? So if alpha is equals to 0, that implies that T of 0x, which is equals to T of 0, and T of 0 is equals to 0. So that shows that the first proof is established. Okay? The first proof is established. And don't forget, our alpha is a scalar. Our alpha is a scalar. So now the second one, the second proof. We shall show that for y1, y2 in R of t, in R of t, we could have alpha 1 y1 plus alpha beta y2 is equally in R of t, where alpha and beta are scalars. Now let's define our R of t, that is the range of the function. The range of the function itself is defined as a set of y such that T of x is equals to y for some x in x. So this is the range of the function itself. So what we actually want to prove is that to show that the range of function is a sublinear space of y. Okay. Now I said we shall show that for, let's pick any two elements in that range, and obviously you can, from this definition, consider y is an element in the linear space y. Okay. Now, and y is a codomain in that space. That is, T taking x to y. So y is the codomain. It is inside this codomain that we have the range of this particular T. Okay. So what we don't want to show now is that the range of function, that range of T now, is a subspace, is a linear subspace of y. Remember, y is a linear map. Okay. Y is a linear space rather. So x and y are linear spaces. So T is a linear map that takes x to y. So that the range of T now will be a sublinear space for the linear space y. That's what we want to show now. Okay. Now, to do that, now let's write. Now, y1, y2 are in the range of T. Beautiful. This implies that for T, Tx1 is equals to y1, Ts2 is equals to y2 for x1, x2 in x. That is, from our definition, we said let y1 and y2 be a range, will be elements in the range. So now say, if we now go back to that, now y2, the element in the range implies, look at the definition. Look at the definition of the range. The range says that T of x should equals to y. So now that implies that T of x1, because when we have y1, y2, we are respectively going to have what? X1, X2. So T of X1 will be equals to Y1, T of X2 will be equals to X2, okay, I mean Y2, for X1, Y2 in X. I hope that is taken. Now, you could equally have, let's say that, you could equally have, also, you know, alpha X1 plus beta X2 will also be in X. Will also be in X. Why? For X being a linear space, you know. So, and by the what? By the linearity of T, we have T of alpha X1 plus beta S2 will be equal to, let me clean this, will be equal to what? Will be equal to alpha T of X1, okay, plus beta T of X2. And from what we have earlier stated, we said that T of X1 should be equal to Y1 and T of X2 should be equal to Y2. So that implies that what? That implies that alpha Y1 plus beta Y2. Can see that you know, that happens there. So which implies that that implies alpha Y1 plus beta Y2 is in what? The range of T. So the range of T is a linear subspace of Y. I hope that is taken as well. What method we use there? We know that since X is a linear space, so and a linear space, you know, have two operations. But it's a linear space is the same as vector space. Don't be confused. So it has the operation of addition and scalar multiplication. So if X is a linear space and we have element X1 and X2 coming from X, so we can have alpha, which are scalars. Alpha and beta are scalars as usual. You know, alpha X1 plus beta X2 is already in X for X being a linear space. And I'll say by the linearity of T, because the T, according to the hypothesis, is a linear map. So we have what? This plus T of that, which is equal to what? This. Okay. So when you factor out your alpha, you get alpha T of X1 plus beta T of X2. So T of X1 already is Y1. T of X2 is what? Y2. So with this now, it implies that alpha Y1 plus beta Y2 is up. Because already Y1, the results is in R of T, which is the range of T. So the result of this thing now has given us this, which implies that it's in the range of T. Okay, let's look at the third result. Let's prove the third result. The third result says that what did I say? If T is 1 to 1, T is 1 to 1. If and only if T of X is equal to 0, and what? That implies X is equal to what? 0. Okay. Now we assume. Let's first of all say that assume T is 1 to 1. Start from there. You assume T is 1 to 1. The T of X is equal to 0 implies T of X, you know, is equal to T of 0. Because 0, which means T of 0 is equal to 0. That's by the linearity of T. Okay? That is, so since T is linear, that's by the linearity of T, T of 0 equals to 0. But T is 1 to 1, according to the definition there. So X is 0. Now, from the linearity of T, we have T of 0 equals to 0. Fine. Now, we now say T is 1 to 1 because that's the basis. So X here, because if you look at the T of the X here, you know, has given us T of 0. So that obviously means that since T is 1 to 1, X is equal to 0. Now, conversely, Conversely, assume that whenever t of x is equal to 0, x is equal to 0. Let's assume that, okay? X must be 0. Yes, x must be 0. Now we want to prove that from the proof t is 1 to 1. I want to prove that. So let's t of x is equal to t of y. If t of x is equal to t of y, we can have what? T of x minus t of y equals to 0. That will give us what? T over x minus y is equals to 0. Okay? I hope that is taken by the linearity of t, which implies what? By the linearity of t now, x minus y is equals to 0. I hope you understand that. Beautiful. So by the hypothesis, x minus y becomes 0, which implies what? Which implies x is equals to y. And when x is equals to y, what are we saying? The proof has been established. The proof has been established because our proof is to show that we have to prove that t is equal to 1 to 1 if and only if this condition is satisfied. So for the last one, I want you to try that and submit right away into my Gmail. I am Dr. OJ. Do well to click on the notification bell so that each time I upload new video, you'll be duly notified. And share and like my video. God bless you.